Welcome to Planetterrian Daily, episode 61, coming to you on May 12th, 2026. Here's your science and health briefing. Fossils long interpreted as early animal trails are now recognized as preserved bacterial and algal communities. Microfossils dating back 540 million years in Brazil were long read as trails left by tiny worm-like animals. Fresh analysis shows these structures are instead fossilized bacterial and algal colonies that include intact cells and preserved organic material. The reinterpretation removes any assumed presence of early animals and resets the timeline for when complex ecosystems first appeared before the Cambrian period. Researchers note that the preserved detail gives a direct view into microbial communities that dominated at that time. This finding also raises the possibility that other supposed trace fossils from similar periods could turn out to be microbial rather than animal in origin. Future fieldwork in comparable deposits may help test that idea and refine our picture of life just before the explosion of animal forms. What other long-accepted early life evidence might need similar re-examination? The preserved cellular detail offers a direct window into microbial ecosystems that lived and died in place. Reinterpreting these structures removes an assumed early animal presence and resets expectations for when multicellular life truly emerged. On a different note, researchers have identified a consistent chemical fingerprint in the distribution of amino acids and fatty acids that living systems produce, but non-living chemistry does not. The pattern holds across Earth samples, even when individual molecules overlap with those generated by abiotic processes. This statistical approach therefore does not rely on spotting any single known biomolecule, such as DNA or chlorophyll. Instead, it looks at uneven distributions that random chemistry rarely matches. The method could guide instruments on future missions to Mars or icy moons without requiring prior assumptions about specific compounds. Now, here's something most people get wrong about the search for alien life. Most assumed detection will require familiar molecules, such as DNA or chlorophyll. That expectation overlooks how non-living chemistry can generate many of the same building blocks without ever producing organized systems. Right now, as you consider what makes something alive, the distinction lies in statistical organization. Living processes create uneven distributions of amino acids and fatty acids that random chemistry rarely matches. Researchers have quantified this difference across Earth samples and shown it holds as a reliable separator. One memorable detail is that the pattern emerges even when individual molecules overlap with abiotic sources, making distribution the stronger signal. Future missions could therefore scan for these imbalances rather than specific compounds. Watch for instruments on upcoming landers that test this statistical approach on Mars or icy moons. Shifting focus to cancer biology, researchers have traced rare tumor cells in breast cancer models that divide far more slowly than typical cancer cells. These slow dividing cells can remain hidden for years after initial treatment appears successful. Their identification clarifies the mechanisms behind dormancy and the late relapses that affect many patients. The work maps how these cells persist within tumors and what allows them to reactivate long afterward. Understanding this persistence may eventually help design strategies to target dormant populations before they cause recurrence. The findings come from detailed tracing in breast cancer models rather than from any immediate therapeutic trial. Next up, simulations of atmospheric escape have set a new lower size limit for planets that can retain atmospheres against stellar radiation. Planets slightly smaller than Earth mark the threshold where gravity can hold onto gases over long periods. The models narrow the targets that telescopes should prioritize when searching for potentially habitable worlds. They also refined selection criteria by focusing on the physical processes that strip atmospheres from smaller bodies. This adjustment helps observers allocate time more effectively on instruments looking for signs of stable climates elsewhere. On another front, the Hubble Space Telescope has captured a massive, lopsided planet-forming disk, nicknamed Dracula Civito. The structure shows strong asymmetry with material concentrated on one side and tall filaments rising from the plane. Enough mass remains in the disk to form several giant planets, making it a valuable case study for disk dynamics. The image reveals turbulence and uneven distribution that astronomers can now compare against theoretical models of planet formation. Such observations add concrete detail to how disks evolve and fragment under their own gravity. Finally, data from the James Webb Space Telescope have produced the clearest map yet of the cosmic web, stretching back to when the universe was roughly 1 billion years old. The Cosmos Web Survey compiled information from over 164,000 galaxies to trace large-scale structure. The resulting map shows how matter clustered in the early cosmos and sharpens models of cosmic evolution. These observations connect the distribution of galaxies across vast distances and help test predictions from simulations of the first billion years. Fresh data from multiple telescopes and fossil beds continue to redefine how we read both the distant past and the conditions needed for life elsewhere. Next time, we'll be watching for further analysis of the cosmic web structures and any new fossil reinterpretations that test the microbial origin hypothesis. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own.